Welcome back. This is Lecture 7a, Compilation, Mapping Quantum Programs to Hardware. I'm Jonathan Baker. In today's video, we're going to cover the basic objects and strategies used for mapping input quantum programs to hardware. First, let's specify the problem and the objectives. The goal of the mapping problem is that for every program qubit, i.e. the qubits used when specifying the quantum program, so for example, we have a quantum program that has qubits A, B, and C with maybe some operations on them. And the goal is to assign that to some hardware. So say we have H1, H2, and H3 as our qubits in our hardware. This is the program. That is, the goal is to write a mapping that takes the qubits on the left and assigns them to qubits on the right. So for example, we might take A to H2, B to H1, and therefore C to H3. We of course can't assign more than one program qubit to the same location on the device. They can't overlap in space, and so the goal is to write a bijective mapping from the input qubits to the right qubits. It may be the case that there are way more hardware qubits than program qubits, but that's okay. But we do need to guarantee that there are enough hardware qubits for all the program qubits. There are definitely some optimizations that can be used to reduce the number of input qubits in your program. It depends on the circuit, though. What makes a good mapping, of course, depends on the objectives. But maybe let's take a step back and ask, why do we care about mapping at all? First, let's recall that in the NISQ era, or the current state of operational devices that you'd find via IBM or other cloud services, is that we can only perform 2-qubit interactions on qubits which are adjacent in hardware. So for example, in superconducting devices, only certain physical qubits are connected via circuit wires through a coupler such as a capacitor. And in trapped ion systems, for example, this means whether or not a laser which performs operations can simultaneously address both qubits at the same time. Say, for example, 2 hardware qubits, so we'll just take a sample ion trap device at a high level, and we have these two traps that are connected somehow. And if we put a qubit in the left one and a qubit in the right one, we wouldn't expect that we'd be able to address both of these at the same time. And so we wouldn't expect to be able to perform a 2-qubit operation on them. So a mapping which performs this will be poor. So therefore, if we map qubits in a poor way, then we may be required to add extra operations in the form of swaps, or generally just take more time to execute the operations we want to do. Let's make this concrete with an example. Let's take a look at our ion trap again. We'll make a new ion trap. This is ion trap 2. And we want to map our input program P up here to this ion trap. We again have 2 traps. And say there's many places that you can assign within each of these traps. So we'll just say 4. So there's four ions in each of the traps. And if we performed a mapping which puts qubit A here, and qubit B here, and then qubit C in the right one, this would be okay because now we can perform A and B in one step, and C on its own in the other trap. But you can imagine that our mapping could have been poor, where maybe B gets put in the left and A gets put in the right. But now we are unable to perform this operation on A and B, and we would need to first do some operation that either moves A into this left trap or B into the other trap. This, of course, gets much more complicated when there's many more qubits. So say A wants to interact with all of the qubits. It also wants to interact with C. And now we have a choice about where do we place them. Of course, in this example, we could just place them all in the same trap since there's 4 options. But you can imagine scenarios where there's lots of qubits and lots of interactions, and now you have lots of choices that you need to make about where things go. There are, of course, several objectives when placing qubits on a device. The simplest, and usually the main objective, is to minimize the amount of distance between frequently interacting qubits. If a pair of qubits interacts all the time in the program, say, for example, in our program, A and B just constantly interact. Of course, a lot of these gates would cancel, so maybe we'll put some things between them. Then we'd want to make sure that these 2 qubits are placed really close together so that we don't have to keep doing this operation in the bottom right, where we have to keep moving A into the correct trap to execute the gate. Other objectives are centered around the minimization of error and accounting for variance in hardware. So for example, most error in the near-term systems comes from additional gates in the form of these swaps or movements, the things used to transport the qubits around. To minimize the total expected error, we want to minimize the total number of gates in the final program, but say we have different amounts of readout error or single qubit error on different qubits, then we might want to choose certain positions over others, but we'll talk more about this in the future. But let's just look at our example again. So say all of the qubits in the left trap have 10x more measurement error than the qubits in the right trap. We would prefer usually then to put most of our qubits on the right so that we can incur less error with measurement. But of course this may also add extra error because we have to keep moving it back and forth. So there's definitely a balance you have to strike between all of these different objectives. It's clear, however, that when current devices are limited and heavily constrained, high amounts of optimization are needed to maximize the probability of program success, whether making sure that highly interacting qubits are together, or we choose the right qubits that have the best error rates, etc. So far, we've relied on an intuitive understanding of dependencies in the underlying hardware. Now, we're just going to more formally define the device connectivity graph, which is used to indicate between which pairs of device qubits we are physically able to execute gates between. So we have a graph G, which is defined by its vertex set and its edge set. And each hardware qubit is a vertex. So say we have a graph. Each of these qubits is a hardware qubit. And then there is an edge between, say, qubit U and V in the system. If I can perform a 2-qubit gate between them. So say, for example, this is a superconducting device. I might fill this out with, many into a grid. But of course, this means that, say I have W down here, the edge UW is not in my edge set. This implies that we no 2-qubit gate. And this would require us to move U to V before we can, because VW is in the set. So we can do that gate. Okay, in terms of communication, the more densely connected our hardware graph is, the more easily you'd be able to execute gates between distantly located mapped qubits. So for example, in this example, the top left qubit and the bottom right qubit are very far away, and this graph is fairly sparsely connected. But if we imagine that all of these qubits are able to interact, then obviously we don't need to communicate this long distance to get there. Instead, we can just directly execute the gate. Okay, let's see some more examples. So for superconducting devices, the general strategy, or the most common structure, is this grid-like that we just saw. So either like square grid, so this is like a 2D lattice. But you can also do some other type of grid. So one common strategy nowadays is to do a hexagon. And there's usually some other like physical constraints on why we would choose one versus the other. So this is like a hex lattice. Obviously, the hex lattice is less densely connected, but it doesn't have as many edges that are like tightly packed in together. So we may not have to worry about something like crosstalk, for example. Okay, so for ion traps, there's multiple strategies for how they implement ion traps. But these are typically much more densely connected. So, for example, usually we expect that traps are fully connected within a trap. So in our 4-qubit example, all of the qubits can interact freely. But in the case where they have limited amount of qubits that they can fit in a trap, we might expect some weak connection between the traps. So if we added an extra trap, And there may be only like a weak connection between these two qubits, which might be much more expensive to interact across versus within the trap. Other models like a linear tape will have much higher densely connected pieces in the middle, like a complete graph in the middle, and then you'd keep having a sliding window of complete graphs, which is hard to depict here, but you can kind of get the idea that each of the boxes I just drew in a row were a complete graph, and I shifted that window. Then I kind of isolate the qubit here on the end, but I add this other qubit to a new complete graph. I want to cover one more important representation for quantum programs. Previously, we've covered dependency graphs to understand the relation between operations. Here, we want to talk about the program interaction graph to better capture the relation between qubits. So once again, we have a graph G, composed of its vertices and its edges. And V is the set of logical program qubits in the computation. So in our example before, V would consist of this example, of this set of A, B, and C. The edges are between vertices V and U if there's an operation between V and U. So in our example before, we had a C naught between A and B in the very first iteration of our example. And so then we would expect there to be an edge between A and B in our edge set. These edges are usually weighted by the number of times that those qubits interact. So when we draw our graph, so say we have a graph, this is our program graph from our example. This would be just weighted 1 because there's exactly one C naught in the original circuit. But say in that more complicated example, instead of 1, we had like 3 gates in there. We would just weight this to say that A and B interact 3 times over the course of the program. This would indicate that these are like much more tightly, they need to be much more close because they interact frequently. We can of course construct this graph just by enumerating over all of the gates in order. It doesn't actually matter for this construction, the order. And then you just end up with a graph where each of the edges in the final graph are weighted by the number of times that we interact those qubits. If we wanted to consider more complex interactions, say a Toffoli gate, we might be interested in writing something called a hypergraph, where the edges, instead of just being pairs of qubits, are instead arbitrary sets of qubits. For the most part, current hardware only supports 2 qubit gates, so we can stick with this model of having only 2 elements in our edges. So using these 2 graphs that we've just defined, the goal of the mapping problem is to efficiently embed this graph, the program interaction graph, into the hardware graph, of course with different objectives. Okay, so let's cover some common objectives used by heuristics or other algorithms to minimize the effective qubit communication. We'll cover other strategies for minimizing device-dependent error in the future. So the first one I want to talk about is edge distance minimization. The edge distance of a mapping can be defined as the distance between the physical locations, so the hardware locations, of each endpoint of the edge in the mapped interaction graph. So say we have our example from before, we have this superconducting hardware that looks like this. Then if I mapped qubit A to here and qubit B to here, then we would consider the distance here to be 1, 2, 3. You could do 2 if you wanted to ignore the last step, because that you only actually need to get to 1 before the destination to interact the qubits in this device. Of course, this is not looking at the distance in some other graph. It cares explicitly about the mapped version of this. So say this is actually mapped to H1 and H6. Then we really want the distance between H1 and H6, not like some other distance between A and B, maybe in the interaction graph or something. So the idea here is that longer distance swap chains, these long chains across the device, can take more steps to complete and are more likely to overlap with other chains that may be moving through the other device in a different direction. Therefore, we incur the additional error from extra gates and possibly scheduling problems with congestion. The effect of this problem on future fault-tolerant devices is less clear. Some devices use a strategy called braiding, which takes about the same amount of time, independent of how far they are on the device. However, we still are maybe hit with the congestion issue, because I might take up more of the device to execute a braid, and then I can't simultaneously execute a bunch of other braids at the same time. Okay. The second objective is called edge density uniformity. And I, of course, am only selecting a couple of objectives. You can think of many more objectives that you might want to use if you were writing your own mapper. These are just a few examples. So, of course, the program graph that we saw before isn't going to map perfectly into the hardware graph. We will always have to make some adjustments as to the placement of the qubits. Even edges which are close together in the program graph can end up being distant or will end up crossing through each other. In fact, when edges of the mapped interaction graph are very close, they are more likely to intersect. So, for example, let's keep drawing my same graph, my same hardware graph, and say I have 4 qubits now, A, B, C, and D. And we know that maybe all of these interact to some degree, but maybe B and D is really heavy. Like this is maybe like a weight 8 interaction, and A and C are also very heavy, maybe weight 9. Then we might have to keep swapping through this network over here because they're very close together in order to make sure that A and C can interact and B and D can interact. This becomes much more of an issue when the program graph or the hardware graph is much larger and things are always crossing through each other trying to interact. In the ideal case, we want to maximize the spacing between these edges. We want to make sure that B and D are separate, A and C are separate. There's of course this complication where A and D also wants to interact and A and B wants to interact, etc. But the idea is that if we could separate them in the ideal case, we would distribute them in the network so that they're spread out and uniform across the device, so that they don't have to worry about this congestion and intersection issue. So notice that for most of the heuristics and objectives we're discussing are in this context of routing. How do we move the qubits? And that's the subject of the next video. But we want to make sure that in our mapping, we prepare the circuit in the best way for any routing heuristics to be able to communicate qubits in the most efficient ways. Okay, finally we'll discuss edge crossing minimization. An edge crossing in a mapping is when 2 pairs of endpoints. So I'm going to just give a hypothetical device, or maybe these are distant. So we have qubit A, B, C, and D. I've dropped my cat notation, and say there's some path through the device to get from B to D, and there's some path through the device from A to C. These could be long or short, and so we would call this an edge crossing. And we're assuming that these paths are the shortest paths from B to D. These are the shortest paths, which are of course easy to compute. This would be common in something like the ion traps from before, where we saw there was that one weakly interconnecting edge, and so all of the interactions between traps need to be routed through that weak interaction. So we have lots of edge crossings there if we have to keep swapping back and forth. These crossings always, but of course not always, we can imagine a scenario where, maybe there's 2 points on the same line and they want to both swap in different directions, that we could, this doesn't necessarily create congestion. We could swap them at the same time and actually use the same swap path to do it. But we could also imagine things where maybe this path is really short and this path is really long. That this one can just happen while these other early operations are happening. So this doesn't necessarily create extra network congestion, but it often is the case that it will, like in this first example. You can also, so one maybe clear example is you can consider devices using teleportation to help increase the density of edges. And if two paths try to use the same entangled pair for teleportation, this of course isn't possible because the resource is consumed. And so we would need to re-prepare in order to use the teleportation circuit again. So once that resource is consumed, that shortest path kind of changes. And so either that second one is going to get heavily delayed, or we need to find some other new path. So minimizing these edge crossings is known to be hard or computationally expensive. And we, of course, will need approximations. So the last objective I'll mention again is error minimization. All of the objectives we've talked about so far attempt to minimize the amount of bad things going on. Is there an increase in time in my schedule? Are there extra gates that we need? And so writing objectives and algorithms to explicitly account for these metrics, the error metrics, is the feature of a subject video, so stay tuned. But it is often the case that optimizing these other proxy metrics like minimizing swap paths or minimizing swap distance is sufficient and much less computationally expensive. There's a wide number of heuristics that you can deploy. Okay, so there's a wide variety of heuristics, as we just mentioned, that one can adapt to create some mapping. Of course, you could always do the trivial mapping where you just assign the first program qubit to the first hardware qubit. This won't usually be very good, unless someone's written the program explicitly for that hardware, which also isn't often the case. Okay, so let's work through one very simple mapping strategy using some basic assumptions. The first assumption is that placing qubits which interact heavily next to each other will ensure that they don't need to be commuted around the device frequently to interact. So if we have that really high edge, like 100 times A and B interact, we want to just make sure that A and B are right next to each other, and then we don't move A and B a bunch. So that they'll be together, and we'll just keep being able to interact as frequently as they want. And then the second is, if we begin our placement in the middle of the device, this will help ensure that we don't run into corners or weird sort of crannies that we can't get out of, and then placing heavily weighted edges far across the device because we had to sort of reset where our mapping was. Okay, so this strategy is really simple. So we'll just assume we have our grid again for simplicity. And then so this is our hardware. And then we'll do our program. And say we have 5 qubits, just quite a small. We don't actually need to know what the program looks like. We'll label these. And we'll give some edge widths. Okay. So the first step is to look at all of our possible qubits and to look at which one has the most interactions with it. So that would be to sum up all of the edge weights that are coming out of it. And so of course B here is the largest with 8 plus 9 plus 10, which is 27. And so we want to place B first. And our strategy, our assumption was that if we place it somewhere near the middle of the device, that'll be best for us. You can imagine that, say that the middle of the device has really high errors and things. You don't actually want to do that, but we're going to assume uniform hardware for now. So we'll just place B somewhere in the center. You can compute the center of a graph pretty easily. And so we just know that this is B, so we'll place B here. And then the strategy proceeds by just looking at all of the possible qubits connected to B in the program graph. So we've already done B. So now we're looking at A and D and C as possible options to map. And we want to map the one that has greatest weight to all of the qubits that are already mapped that it's adjacent to. So when we computed it for C, we'd only consider the weight to B because B is the only one mapped. We wouldn't add this extra weight to D because D is not yet mapped. So here, of course, we'll place C. And so C should go somewhere next to B. We might choose some complicated heuristic, but say we want to stick to the center, so we'll just place it here as C. So now C is mapped, and so now we still have A that we can consider, which still has weight 8. It only was connected to B. It was not connected to C. But now qubit D has weight 9 to B and 2 to C, so its total is 11, which is better than A. So we should place D in the position that minimizes the total distance to all of its targets. So this is place D. or C rather. And we want to weight its position by the weights of its graph. So for example, we don't want to place D really close to C. This is bad, because there's now a really long distance between D and B. In fact, we prefer to place it closer to B. And so we would compute something that weights the distances based on its own weight in the interaction graph. So we end up placing D here. And then again, we would just proceed until we have all of the qubits mapped. So A would be next, and it should be next to B, so say it ends up here. And E only needs next to D, so we could place it here. Of course, this graph on the right couldn't perfectly be mapped into the graph on the left, because there's none of these triangle structures in the target hardware. And so necessarily there will need to be some amounts of swaps to interact D and C in the program. Of course, you can always make this strategy much more complicated. This is just a very simple one to account for other parameters you might want to. One might be that maybe B and C don't interact at all in the first. All the other interactions actually happen first, and so we don't necessarily care about where B and C start with. We only care about them at the end, for example. You might want to account for some temporalness, and then this program graph isn't going to be completely helpful on its own. Okay, let's talk about one more mapping strategy which can better take advantage of those three objectives that we talked about before, and it's called force-directed annealing. So in this procedure, we're going to iteratively calculate cumulative forces, some value for each of the vertices, and then move those vertices according to those forces. So you can imagine that if I have a vertex and there's some really big, force in this direction, that indicates that for some reason this vertex needs to be moved somewhere else on the device, like up in this direction. Okay, so there's three forces that correspond to the three objectives that we had from before. The first is vertex-vertex attraction. So and this is used to reduce edge length. So for example, if I have two qubits that are far away, so this is like a large distance, then we would want to make weights going close to each other. We would want to add forces that push them close together because they interact frequently in that interaction graph. So say A and B, the weight of A and B in the hardware is like 100 or something, then this force would be really big. It would really want to push those two together. Okay, the second is edge-edge repulsion. And so this is to account for that edge density issue. And so if I have two edges that are like this, then there would be a force that pushes these qubits away from each other to make sure that those edges don't necessarily have to intersect or cause congestion. And then the third is this magnetic dipole edge rotation thing. So essentially what we do is for every edge, right like this, we assign a polarity, so plus or minus, to each of these qubits. So we do this. And essentially the goal is to then push these two things away from each other because they're, or actually not that way. To push these two things away from each other. And then eventually it'll rotate this one away from here, and that'll reduce the edge crossing. We can, by adding this extra force, we're trying to push half of it away, and this of course will get up like this. So this will end up rotating this edge away from the other edge and reduce the edge crossing. So using these three forces, we can compute some total force on each of the qubits or the vertices, and then move the vertices through the network based on these forces. The general annealing process's goal is to then reach some steady state where there aren't any strong forces pushing qubits into new locations. At every step, we're able to recompute these forces continue and proceed until convergence. This strategy is often effective, but only guarantees a local minimum in terms of our objectives. An optimal solution to the mapping is much harder. In today's video, we've covered a high-level overview of the mapping problem, formalize some important underlying objects, and discuss some basic objectives and strategies. There are so many adjustments you can make to these heuristics, and there's a large amount of research in this area if you're interested.